recording now? Yes, it's recording now. That's good. Okay, so I'll just go back to the share screen. And cancel that and share it again. Okay, can you all see that then, folks? The basic physical chemistry 4.
Yeah.
Right, I'll just maximize that as well. Let's go there. Okay, so this morning we're going to finish off the basic physical chemistry series. This is Phys Chem 4, which follows on from last time when we did the molecular weight and molecular weight averages. So we've done all that. So we're just going to finish that off with a discussion between absolute and what's called relative methods for determining molecular weight. And then we'll cover a bit about conformation, particularly conformations of linear molecules. We've discussed proteins before, but now linear molecules like DNA and polysaccharides, carbohydrate polymers, and how we quantify them in terms of a parameter known as the persistence length. So that is the plan for this morning, and we'll just okay. So in terms of molecular weights, molecular weight measurements, there's two classes of measurement of molecular weight. There's the so-called absolute group of methods and relative methods. And you've already met one absolute method, that is osmotic pressure. And we referred to others like light scattering and sedimentation equilibrium. When we had the demonstrations last week, I showed you some of the relevant instrumentation. But absolute methods do not require a comparison with standard molecules of known molecular weight. They don't require a comparison. They give you the molecular weight directly without referring to comparisons with other materials of known molecular weight. I mean, by all means, you can use materials of known molecular weight to check the correct functioning of the instrumentation to give the right molecular weight back, but they're not required as standards for measuring materials of unknown molecular weight. And we've already learned about one method, that's osmotic pressure. And that gives us what are called number average molecular weights directly, because you've got a polydispersed or heterogeneous material. It'll depend on the number concentrations of the different materials, which dictates the average. That's called a number average molecular weight. And other examples of absolute methods include the light scattering, the total intensity light scattering, the SEC-MALS device I showed you last week, and sedimentation equilibrium using the analytical ultracentrifuge. And these are methods which give the weight average molecular weight. So you're not required to know these methods in any detail, just to know that they give the weight average molecular weight. And you need to know this one because we've covered that in the lecture. So these are absolute molecular weights, not requiring on comparison with standards. The relative methods, they do require comparison with standards of known molecular weight, and usually also of a similar conformation to the macromolecule being analyzed, because these methods not only depend on the molecular weight of the molecules, but also on the conformation. So if we're using comparison standards, we need to have standards of the same or similar conformation to the macromolecule being analyzed. So if you wanted to measure the molecular weight of a protein with these methods, you wouldn't use DNA as your standards. You'd use other proteins, other globular proteins, if it's a globular protein that you're studying. And we often give the symbol M with a subscript R to indicate these relative molecular weights. And if you're using these, you need to stipulate what standards they are relative to. There's gel filtration. Again, we're not going to cover that in this course. That can be covered if you do the biotechnology MRes course. Then we'll go into this in detail. But just to be aware that these gel filtration methods, size exclusion chromatography, SEC, or another name for this is gel permeation chromatography, GPC. These are relative gel filtration methods, and they work reasonably well for globular proteins. Again, the calibrating materials need to be stipulated. So you calibrate your columns with globular protein standards if you're looking at a globular protein. It's a bit more difficult when you're looking at other types of molecules like polysaccharides or synthetic polymers because of the difficulty in getting polymer standards of the right conformation. But if measuring molecular weight using this technique, and you say that your results are relative to polystyrene standards or polylan standards, then that's absolutely fine. Other people know what they refer to. Another popular relative method is gel electrophoresis, particularly sodium dodecyl sulfate gel electrophoresis for the separation of proteins and the measurement of molecular weights of proteins. So these two provide relative molecular weights, and by treating, but you compare with standards, but by treating the proteins with a substance called sodium dodecyl sulfate, you confer on the proteins all the same linear conformation. You need to use thiol reducing agents as well, but you can confer on the proteins similar conformation. So the comparison with standard proteins is valid, and we'll be doing that next week. So that will be the relative method we'll be focusing on. So in this course, we focus on one absolute method, which is osmotic pressure, and one relative method, which is gel electrophoresis for measuring molecular weights of molecules. And then we'll see what limitations the gel electrophoresis has in terms of the types of molecules that you can look at. All right, folks, so absolute and relative molecular weights. Just a few words about conformation, and we say the reason why I'm giving this now is when we do the polysaccharide lecture, we'll look at this in a little more detail. So we can represent conformations of linear types of molecules qualitatively using what's called conformation zones. For example, zone A is a very rigid rod type of molecule with little flexibility. Zone B is a rigid rod but with some degree of flexibility. Zone C is a semi-flexible molecule like pectins, which comes from the cell walls of fruits and is used in jams, jellies, and other applications. In fact, many applications in biopharma. So this has some degree of flexibility, so, more so than a xanthan, another polysaccharide, and schizophyllan, another polysaccharide. These are all polysaccharides. This is a very rigid molecule. It's got basically 3 helices intertwined to give it the strength. Xanthan has apparently got 2 helices. That's why it's also a rigid type of molecule, but with some flexibility. And then you have this linear semi-flexible pectin. And zone D is a very random coil, and very flopsy types of molecules. And dextrans and poululans, these microbial class of polysaccharides, have this very high flexibility. And then zone E corresponds to very highly branched globular types of macromolecule. Of course, proteins would be zone E, but from polysaccharides, highly branched amylopectin or glycogen molecules would fit in these zones. And the way you establish these zones is using various combinations of hydrodynamic methods, including imaging as well. That can also be used, but these methods can tell you the type of conformation. So this is if you like, a more refined form of the Haug triangle representation. So we have 3 extremes: the sphere, rod, and coil at the hypothetical ends of this triangle. I think we covered that in the macromolecular size and shape lecture earlier on in the course. These are the conformation zones then, which give a qualitative measure of flexibility of a macromolecule, particularly a linear macromolecule. For more quantitative measures, we use a parameter known as the persistence length. So this refers to linear types of molecules. Here's a linear molecule here, and its chain length or contour length is L. And what the persistence length is, it's the projection from the end point of the chain. So you drop a perpendicular, a right angle, to the original direction of the start of the chain. And this distance here to here is known as the persistence length. In the limit that the chain length goes to infinity. So the persistence length is defined as the projection length along the initial direction of a chain of length L in the limit that L goes to infinity. This was a perfect rod molecule, then it would stay in the same direction. It wouldn't deviate in solution. It wouldn't change its orientation. It wouldn't change the way the chain is arrayed. It would stay in the same direction. So in the limit that the contour length goes to infinity, then the persistence length would be infinity. So the theoretical limit for a perfect rod for the persistence length is infinity. Conversely, with a completely flexible coil, okay, so the molecule is completely flexible, so it'd be flopsying about with half the time in this direction here, in the positive direction, and the rest of the time in the negative direction. Okay, so average over a period of time, the persistence length would be, well, an average of all the positive directions, the negative directions, so the average would be 0 for a perfect coil. So the persistence length gives us a measure of the flexibility. Practically, the upper limits are for macromolecules, polysaccharides in particular. The maximum value for the persistence length is about 200 nanometers. That corresponds to a rod. And the minimum value is about 2 nanometers coil. So a molecule like schizophyllan or xanthan would have a persistence length approaching 200 nanometers, whereas something like pullulan or dextran would have something like 2 nanometers. And the values in between depends on the degree of flexibility. So this persistence length value will give you a quantitative measure of the flexibility of a molecule. With numbers down here, very flexible, and numbers up here, very rigid. So we'll cover that again when we do the polysaccharides lecture a little bit later, and I'll give you some examples of that. So that, I know it's been very short, but that just rounds off the Phys Chem series of lectures, and we're now in a good position to consider the properties of polysaccharides, which can have a variety of conformations, conformation flexibilities, and also, as I said before, because they're not coded by a template, just template like proteins are, they will have a distribution of molecular weights. So polysaccharides provide a good class of molecules to try out some of the things we've been learning about in terms of the Phys Chem lectures. Okay, so with that, I will stop there. Just stop the recording.